Okay. Well, we have not widescreen, but at least better resolution today. So it's a good start. Oh, whoa, I made myself bigger. Woo! Okay. Didn't mean to. Well, we are now doing actual system dynamics stuff because I guess that's this class, so we should do it. I don't know. Let me know if you don't want to. We just stop. Okay, so I am going to start us off with a chapter called Qualities of Transient Response. Before I start going, if you are in this class and you did not take mechatronics and you've never taken mechatronics, there is a Slack group that's discussing that fact. Get in it today. We want to make sure that you are knowing what you're getting in for. You can do this class without having mechatronics. It is hard, I will admit. Okay, so chapter 1, Qualities of Transient Response. So recall that a stable system's transient response is a summand of the response that decays to zero. Conversely, its steady state response is the sum of those that remain, as shown in figure 1.1. So remember that the response of a system is typically found from its mathematical model, which is a differential equation, by solving that system, and the solution is the so-called response. So the transient part of that response, let's say the initial condition of the system started out at 10. 10 what? I don't know. Just 10. Started out at 10, and it decays. Its transient response is this region that has this sort of decaying trend to it, right? You could draw this line, and my God, that is a pretty decent line. A little wavy, but yeah. So that is sort of the decaying trend, and then you notice that trend is kind of over, and it sort of flattens out here, which was not as pretty, but the flattened part. Notice that there's this sinusoidal aspect, and so in this figure, what I'm plotting here is actually the response of the system to an initial condition, 10, and to some forcing, okay? So the forcing is clearly sinusoidal because what's remaining in steady state is a steady sinusoid, okay? So you will have seen this from mechatronics or from solving a differential equation when you have an initial condition and a forcing function. Okay. So an inhomogeneous differential equation. So the transient response is distinct from the steady state response. And once the exponential decay has damped out, we have the steady state remaining. It doesn't have to be static. See, it's still time varying, it's still a sinusoid, but the decay is gone. So that is how we differentiate between the transient and the steady state response. Exactly, precisely where this transition occurs is a murky idea. We don't really have a precise definition of where that transition occurs because an exponential decays forever, right? It's actually never, it just approaches in the limit zero, so a decaying exponential. So it's always there a little bit. So we'll say for a first order system with a time constant tau, maybe 5, 6 time constants, we say, that's when the transient response is done. Okay? So this is something that is kind of a review for most of us, but good to sort of refresh that memory because I know that Christmas just sort of like beats the information out of your brain, so got to get it back. Awaken those neurons, right? Okay, so in this chapter we explore the qualities of transient response, that is the ways we describe it, okay? We know how to solve for it, but now we're going to actually think about how to understand what it looks like in a deeper way. We're going to focus on characterizing first and second order linear systems. Not because they're easiest, although they are easiest, but that's not why we're choosing to study them. It's because nonlinear systems can be linearized. So even though a lot of systems are actually nonlinear, we can linearize them about an operating point, right? So an operating point being, for instance, like a pendulum problem is something that can be nonlinear. However, you can linearize its behavior about an operating point. Say straight down might be an operating point that you could linearize about, and the behavior near that point is approximately linear. So that's why we focus on linear systems, because even though a lot of stuff isn't linear, we can approximate it as being linear for some operating regime. And so that was the linear part. First and second order, the reason we do that is because higher order linear system responses are just sums of first and second order responses, or at least they can be considered to be sums of first and second order responses, making everything look first and second order. Well, many things at least. Not everything actually looks first and second order, but you can take the characteristics of first and second order responses and look at like a 10th order response, and things kind of look similar to first and second order responses. And that's because they can be they are just composed of first and second order responses summed together. And typically there's like one or two dominant characteristics that come from the roots of the characteristic equation. We're going to use this term characteristic, and it's really meant in that sense, and we'll talk a little bit more about what sense that is as characterizing a system. So, in this chapter, we primarily consider systems represented by single input, single output, ordinary differential equations, also called IO-ODEs, with variable y representing the output, dependent variable time, over here, t, variable u representing the input, forcing function f, constant coefficients ai, bj, order n, and for m being less than or equal to n being an integer, positive integer of the form this. So 1.1a and b gives us our sort of starting point for all of the systems we're going to consider in this chapter. Okay? This is one mathematical representation of a system. It is a linear, ordinary differential equation. Okay? I draw it out in all of its glory because we want to do things in general when we can. So this is an nth order system. So you could have, so if it's an nth order system, it will have an nth time derivative of y showing up in it. So I think for most of us, our differential equations always use y as being the output and u as being the input. I mean, it's pretty standard notation, so that should be familiar to most people. Dealing with nth order systems is actually not as scary as it looks. I know this is scary looking. I mean, I look at that and I go, I don't know, there's a lot of symbols happening. But the nth time derivative of y, that's a really big circle, it didn't need to be that big. This is the n minus 1th time derivative of y. So like, say it was third order, it'd be like third time derivative, and now it's second time derivative. And then this is a coefficient, so that could be like 4, for instance. First time derivative of y, 0th time derivative of y, which is to say not a time derivative at all. All of these having their own coefficients. Notice that the coefficient here is 1 on the nth time derivative. That is our standard form of this equation. You can always make that 1 by dividing the entire equation, if it's not 1, dividing the entire equation by whatever is there. So if 7 is right here, divide everything by 7, and you're good. It will be 1. I mean, maybe it is. You should check. Okay. All right, so that's the left-hand side. The right-hand side, I just put F here because we're going to use that term forcing function to represent the right-hand side of the differential equation when it's in the standard form. The right-hand side has all the stuff that doesn't have a y in it, right? So all the y stuff is on the left-hand side, and everything on the right-hand side does not have a y. It's going to have a u, or potentially it could have just a constant. So we have this expression for the right-hand side, f, and we call it the forcing function. Okay, that's what I wrote right here, forcing function, f. So forcing function is a linear combination of the input u and its time derivatives. Okay. A lot of times our systems don't have time derivatives of u in them, and we just have u multiplied by a constant. However, sometimes we do have time derivatives of the input, so we have to keep that in mind as we do our analyses. So this is kind of the mathematical representation we're going to use for this chapter. And next chapter, we're going to switch gears to state space models again. So for those of you who are in mechatronics, state space models will be familiar to you. But for this chapter, we're just sticking to the good old-fashioned input-output ODE, which describes a lot of systems. Okay, any questions on this? All right. So